section 14.1b, now we're going to work with those iterated integrals and see how it ties in with area. We're going to look at area of a plane region in a new way. So here I have a drawing on the left hand side where you have the area between two curves, and we're going to call that region R. So from what you're used to before, we have this integral up here at the top, the integral from a to b of g sub 2 of x minus g sub 1 of x dx. Now we're going to look at the area using this iterated integral, and it's going to be called a double integral. Notice we're going to have integral from a to b and another integral from g1 of x to g2 of x, and then we have dy dx. This inside part over here is going to go first, and when we integrate dy with respect to y, we end up with y evaluated from g1 of x to g2 of x, and when we plug those in, notice how it just becomes g sub 2 of x minus g sub 1 of x, which is what you're used to. This is what is referred to as regions that are vertically simple, because we are summing up all the rectangles from left to right, and they are all vertical pieces. We can also take a look at two curves, h2 and h1. Here, notice on the inside we have our integral from h1 of y to h2 of y dx, and then the dy is on the outside. This one is what we refer to as horizontally simple, and then it works out the same way. This is going to end up being the integral from c to d of h sub 2 of y minus h sub 1 of y dy. So let's practice with a few examples. Let's find the area of this rectangular region, and we're going to use an iterated integral for this. So this is going to be a really simple region, and I'm going to show you guys some strategies for how to approach this so that when you're not doing such a simple region, it'll be much easier for you to do. So I'm going to calculate this little region right here. Let's take a look at the bounds. Let's focus on the bounds of x and y. The x coordinates within this little region are bounded between a and b, and the y coordinates in this region are bounded between c and d. So I'm going to say the integral from c to d, and that's for the y's, so that's going to be dy. And then I'm going to have my second integral from a to b, and that's going to be dx. Now we're not going to write anything here in the meantime because we're just doing area, so that's actually just going to be a 1. And we would integrate this just as usual. Now some of you may also have a question as to whether or not we could write it the other way. We could write the integral from a to b on the outside and have on the inside integral be c to d and then a dy. Let's find the area of the region bounded by f of x equals to sine x and g of x equals to cosine x between pi over 4 and 5 pi over 4. So let's take a look at this graph. Sine x, cosine x. Now if I want it between pi over 4 and 5 pi over 4, hopefully you're still familiar enough with the graph of sine and cosine to realize that the sine function value will always be on top for that particular interval. So up here at the top we have y equals to cosine x. Down here on the bottom we have y equals to sine x. So we'll be able to write out our iterated integral as a vertically simple section because we have our rectangles standing up. These rectangles are going to be summed up from pi over 4 to 5 pi over 4, and the function on the bottom is our cosine x, and the function on the top is our sine x. So I forgot to write it over here, but if you think about your bounds, we have pi over 4 to 5 pi over 4, and our y values are bounded between the sine function on top and the cosine function on the bottom. Let's find the area of the region bounded by y equals to x and y equals to x squared, but let's only do this in quadrant 1, and I want us to actually find this using both the vertically simple method and then the horizontally simple method. So here I have my parabola and here I have my line. They intersect at the point 1, 1. And if we're going to look at these as vertically simple sections, let me draw those little regions, and let's consider our bounds. X from the left to the right is bounded between 0 and 1, and the y's, what is it bounded on the top and the bottom by? It's bounded on the top by the line, so x, and it's bounded on the bottom by the parabola, so x squared. So the x's, 0 to 1, and the y's are x squared to x. Now let's work this one out. The integral of a dy is going to be a y, so it's going to be y from x squared to x. So I'm going to have x minus x squared dx. So that's 1/2 x squared minus 1/3 x cubed from 0 to 1. So I have 1/2 minus 1/3, which is going to be 1/6. Once again, I'm going to draw the parabola and draw the line. Their point of intersection is still 1, 1, but our regions are now going to go horizontally, and I need to think about these functions as x equals to y and x equals to the square root of y. So let's consider our bounds for y and our bounds for x. So our y values are going to go from all the way from the bottom to the top, so 0 to 1. And our x's, notice each of these little horizontal sections are bounded on the left by the line and bounded on the right by the parabola, square root of y. So when we write out our iterated integral, this is horizontally simple, so it's going to be dx dy. We're going to write 0, 1 here on the outside, and y square root of y here on the inside. One other thing I'd like to point out to you, when you're completing and writing out these iterated integrals, you're going to notice that the integral on the outside always has bounds that are constants. Example 4, I want us to find the area of the region bounded by y equals to x squared and y equals to x plus 2. So again, I've got the parabolic region, y equals to x squared, and y equals to x plus 2 this time is a line with a y-intercept of 2 and a slope of 1. So you need to make sure you know where these two intersect in both places. It's going to be -1, 1 and 2, 4. See if you want to approach this with horizontally simple sections or vertically simple sections. In this case, your best bet is going to be vertically simple sections. So let's think about our bounds. These little sections are going to go from -1 to 2, and our y values, what's on top of the rectangle and what's on the bottom of the rectangle. The parabola is on the bottom and the line is on the top. So we're going to have the integral from -1 to 2, and that's dx. Then on the inside of that, we're going to have the integral from x squared to x plus 2, and that's dy.